Okay, so you know that next Wednesday we don't have lectures because of the degree day. Okay, so next Wednesday no lectures. Okay, perfect. So the next one will be on May 20. And May 20, please bring your PC. So we continue with, we start with the first exercise in R. Okay? Second issue, if on May 20 some of you would like to deliver a short presentation, I think it would be a good idea, a good thing. And you may select a topic by yourself. My suggestion is if you are whatever, from Italy, from another country, if you present something related to what you see close by your home, or everywhere, meaning that you could go on the beaches here and present a problem to solve, or present techniques that are used to protect the beach. This is fine. This is my suggestion. Just look around, and if you find something that is related to what we are talking about to present, the only thing that I ask you is look for something technical, okay? So you may talk about, as I said, beach protection strategies from a technical point of view. Not extremely technical, but not descriptive, okay? It's not just enough if you go and you take pictures of the beach. Or it's enough, but you should elaborate on that from a technical point of view. So don't be concerned. This is just an exercise that we do, and it's about 5 minutes presentation, so 5 slides. And if you want to take advantage from this opportunity, just let me know in advance. Send me an email, or through the forum. But through the forum you reach everybody, which is fine. I would prefer the forum, actually. Send me I would prefer the forum so everyone knows what's going on. Send me an email for the topic, for booking your presentation. And if you need any suggestion on the topic, like you want to get my opinion on it, you can send me an email. It's not necessary. And my suggestion is just try, don't be shy, don't be concerned. But if you want to get my opinion, this is fine as well. You send me an email and I tell you. Or if you want to get suggestions, like I'd like to deliver a presentation, but I don't know the topic I should talk about, I can give you some suggestions. But first suggestion is, for instance, today we discuss a very technical, or let's say a technical issue, estimating sediment transport. This is the issue. There are several links on the web page. You may follow the links and expand on what we say today. This is perfectly fine. And as I said, it's a very nice experience, so take advantage of it. Maybe that we will serve like 20 minutes at the beginning of the lecture to allow 3-4 people to talk. But my experience is that usually students are a bit concerned about it, and I have to press a little bit. So, yeah.
But you have to make a job, work just for a beach, or for example, protection of a pier?
Of a? Pier. No, that's fine. Also, everything is related to offshore engineering or coastal engineering is okay. Not really everything. I mean, don't talk about oil and gas. This is not relevant here. But everything is relevant to ocean engineering, and coastal engineering is fine.
Well, for example, I'm coming from Como Lake.
Yeah.
And in our lake we have a problem related to a pier because there are wind problems and wave problems from vessels. It should be possible to have a...
I mean, when I say coast, it's also coast of lakes. It's no problem. And pier protection is perfectly fine. Harbor engineering as well is okay. Okay. I would say that the first opportunity may be next time, March 20, but we can also wait. I mean, even the following lectures, there is no, any time we need is fine, but keep in mind that today is my 3rd lecture, I have 4 more, so, because we have 5, but one will be delivered by one of our assistants, Gabriele Gaia, data, and therefore I have 4 more. You have 4 more lectures with me, not so many. So this is why I say just start and taking advantage of it. Okay, so today we continue talking about coastal hydrodynamics and morphodynamics, but today we focus on sediment transport and impact on beach morphology. You know that sediment transport is the main driver of beach morphology. Today we try to get into the details of mathematical models that we can use to study the evolution of beaches after sediment transport. So I am skipping the first part of the lecture because you already know about it. Keep in mind the main definition, what is, of course, a wavelength, a wave frequency, wave period, and mind the difference between wave height and wave amplitude. Amplitude is half of the height, okay? The height is an elevation difference between the crest and the through, which is also called the chest, wave chest. And this is the height, so it's not shown here, but let's say, yeah, it's shown in green. The amplitude is half of it. Keep in mind, because even for myself, when I start, I have to pay attention not to make confusion between these 2 terms. And then we spoke already about these other terminologies, because I anticipated it, what is shoaling, and remind the breaker line. Shoaling causes the waves becoming higher and higher. At a certain point they break. When they break, you have a big change. The wave is a transfer of energy, not transfer of mass. But after the breaker line, waves commute and become they turn into a transfer of mass of water. This means that as soon as they turn into the transfer of mass mode, they have the capability to move sediments. Sediment transport is mainly originated after the breaker line, after the waves break. Okay, so you understand sediment transport originates from the interaction between waves and the seabed, of course. Because this interaction causes friction, which means a bit of sediment transport, causes shoaling, which means wave breaking, which implies sediment transport. Okay, we already talked about the berm and about the dune. Okay, now let's talk a little bit about waves. And I know that you studied waves already, but let me just remind you what we are talking about. So, let me just get also the PowerPoint, just 1 second, because it is useful, it's much better than reading, okay. Okay, so, waves. First of all, what we are talking about? We are talking about wind waves. There are other types of waves, and we may remember the waves that are generated by currents. We usually don't consider them, but let's keep in mind that sometimes we may need to take them into account. Also, there are waves that can be originated by other drivers like tsunamis. We don't talk about them, but just keep in mind that waves are not only originated by wind. There are currents, there are tsunamis, there are boats. Big boats can originate quite significant waves, etc. We are talking about wind waves. How do they originate? It's very simple, you know that. There is the wind blowing over the sea, and the distance over which the wind blows is called the fetch. I'm not sure whether you already know this term. Sometimes we speak about the fetch of the waves, which is the distance along the sea the wind blows over. Okay? And then the friction between the wind and water originate these waves. In open ocean, again, these waves are not a transfer of mass, they are a transfer of energy. Basically, water is pushed up, but not moved forward by the winds. It's pushed up. And therefore, the fact that the water is pushed up, it means that it accumulates energy that is transferred in the wave propagation direction by causing a downward traveling of the wave, and then by traveling downward, the wave accumulates kinetic energy and therefore pushes up again the water, the neighboring water. So it's a transfer of, again, energy, and implies that water goes up and down. And you can realize it if you swim and you go offshore and you get into waves, you clearly see that you don't move forward towards the beach or toward offshore. Basically, your movement is an up and down. If you get closer to the coastline, then after breaking, then you experience really that the waves are bringing you towards the beach and maybe back sometimes. And this is dangerous because keep in mind that sometimes when waves break, they originate a transfer of mass towards the beach, but then water comes back. And then there is a movement back and forth. And sometimes when water comes back, may concentrate in a small part of the sea, originating a return current with the offshore direction, which is called rip current. And this may be dangerous, because if water concentrates, swimmers can get trapped into the rip current, and they might be not able anymore to reach the beach. Some people die, get drowned for this reason, and it's just due to the fact that the water flow, after rushing up the beach, after they run up, when it comes back, concentrate in a small part, and therefore, people that are caught into this current may have some problem reaching the beach back. So, again, let's go back offshore. The wind blows over the fetch, originates the waves, and then the waves can travel thousands of kilometers, and they continue traveling even after, for a long time, even after the wind ceased. Ceased means and the pronunciation was not correct. The wind stopped. The wind stopped. And when we deal with waves that were originated by a fetch that is very far away, we talk about, we name these waves swells. Okay, these are waves that originated very far away and are traveling because the energy that was accumulated by the waves dissipates very, very slowly, because there is not much friction. When you are in open ocean, waves, don't experience much friction with the seabed. And therefore, given that there is really low friction, makes the dissipation of energy very, very slow. And this is why waves can travel for thousands of kilometers. This is the reason. And I'm just explaining the terminology to you because I'm not sure that you know all of these terms, and it's useful that you know the terminology, because just, in the future, when you listen about something, you may not remember what it's about, but you understand that it's something related to waves, and you don't feel uncomfortable. When you talk with somebody about engineering, about technical terms, and you realize that the other person talks about something that you really don't know, you get very uncomfortable. And therefore, I want to provide you a very extended overview of the terminology, because in my experience, if you know the terms, you may not remember what they are about, but still, you don't feel as much uncomfortable as you really don't know anything about it. Okay, now, what is the force that causes the attenuation of waves, it's gravity. In absence of gravity, probably the waves will travel forever, and given that there is gravity that tends to re-establish an equilibrium condition, they attenuate in the long term. And therefore we talk about, sometimes we use the term gravity waves. We may say wind waves, because wind is the driver, but another relevant forcing is gravity. So some people say gravity waves to distinguish them with respect to sound waves or light waves, etc. So sometimes we call them gravity waves. Okay, and what are the main drivers that originate wavelength, the type of waves, wavelength, amplitude, frequency, and there is wind speed and duration, and the length of the fetch, the width of the area affected by the fetch, and this sea depth, because as we have seen, interaction with the sea bottom originates friction and therefore loss of energy. So let me see if here we don't see a picture that I want to show you. I said that waves are mainly transfer of energy, and particles, I said, go up and down, fluid particles. Actually, this is not really true. There is some minor movement of fluid particles along spirals, and this movement is more pronounced for the fluid particles that are close to the sea surface, and this figure explains how fluid particles actually move. And you see that there are these spirals that are the trajectories of the fluid particles, and they are originated by the so-called Stokes drift. We don't discuss about it. But again, what I wanted to say is that this is, we can basically neglect this kind of mass transfer along the wave direction because it's very limited. So basically we neglect it and assume that until the breaker line, particles just move up and down. But just look at it and note that close to the surface, the movement along the wave direction is more pronounced, and it gets negligible as you go in depth into the sea. Okay, so the main behavior of waves, you already know that. And we talk about wave amplitude, length, period of frequency, and direction. These are the main behavior. And keep in mind that we need to describe them. If we want to make any computation and if we want to make any assessment of the impact of waves, we need to describe these behaviors. We need to characterize the waves. And therefore, it's extremely important the direction of waves. If it is a cross-shore direction rather than in a long-shore direction, so I think it's clear, but let me just remind you. If this is the coastline, okay, this is cross-shore, and then this is along shore. It is extremely important. The effect on the beach, as you can easily understand, is completely different. And you will see that we will distinguish between a long-shore sediment transport and cross-shore sediment transport. We will treat them separately in a few minutes. Then we need to describe the period, the length, and the amplitude of waves. How do we describe them? By observing waves and by monitoring waves. We will dedicate some time, a small part of a lecture, to sea wave monitoring. Sea wave monitoring allows us to understand what are the dominant behavior behaviors of waves in terms of direction, period, length, amplitude. What we need to know is what are the dominant behaviors. Of course, there is not only one behavior, it would be too easy. We may have different type of waves, depending on the direction of wind, depending on the weather. But usually we can identify, season by season, dominant behaviors, which are those responsible for the evolution of the beach. It's like when you talk about rivers, usually we know that rivers have a variable flow, but we identify a dominant flow, which is the flow that is responsible for the river behavior in terms of morphology. The same here. We need to identify what are the dominant waves, dominant wave behaviors, and we define them as those responsible for determining the morphology of the beach. Waves are a random phenomenon. Waves are not deterministic. Keep in mind the difference between a deterministic process and a random process. And let me give you two examples. If I drop this pen and I want to start the movement of the pen towards the floor, this is basically deterministic. I can describe it very precisely. There is a one-to-one relationship, if I drop it, between time and position. Of course, I need to take into account the resistance of air, the friction of air friction, etc. But in an ideal situation like this one, if I drop it, I can use a relationship, an analytical relationship, which we know actually, to describe the dependence between time and position. This is deterministic. Of course, you may say, yeah, there is some randomness, but still, I mean, the precision with which I can describe position in time is very, very high, okay, if not exact. So, deterministic means that there is a one-to-one relationship between input and output. Okay, now let me take a coin and toss it, and then I want to determine if at the end of the story I get an head or a tail. You may say that it's a very similar process. It's very similar. It's the movement of a body in the air. But if I toss the coin, I cannot really determine with precision what are the drivers, what are the forces that I exert on the coin. And keep in mind another determinant of randomness is the initial condition. In order to study the movement of the coin or of a dice, I should know the initial position very precisely. I should know with precision what is the force that I am exerting on the coin, what is the angle of my toe when I toss the coin. So it's impossible to determine with precision, it's impossible to measure with precision all these drivers, initial and boundary conditions. So even if the process is more or less the same, because it's a movement of a body that is subjected to gravity and to external drivers, in this case, we cannot describe it with precision, and therefore we say that the process is random. Tossing a coin is a typical example of a random process. This doesn't mean that you cannot predict it. Actually, I can predict what is the outcome of tossing a coin. With 50% probability is an head. With 50% probability is a tail. So I can predict it, but not with certainty. There is not a one-to-one relationship between the position of the coin, the position of my toe. In principle there would be, but it's impossible to apply this one-to-one relationship. So keep in mind, because randomness doesn't mean that we cannot describe a process. Randomness simply means that we cannot predict with precision. So this is the definition. Some people say randomness implies that we don't understand. Absolutely wrong. We understand perfectly what is the process that drives the coin while flipping. But we cannot predict. With waves, we cannot predict. We cannot say tomorrow I will have a wave with wavelength assigned with frequency period. Keep in mind, because The approach of the engineer is completely different. When you have something that you can predict, like you design a building, you can predict basically everything. If it is a civil building, you have the loads that are dictated by law, you have the wind forces. Also, you know, this is a random input, but still you can transform it in a deterministic Damax. You know that the effect of the earthquake, and then you come to a very precise conclusion. When you talk about predicting weather, predicting waves, you cannot predict. You may get an idea in terms of probabilities, like tossing the coin, and you get this idea by observing. But waves are what is called a random process, are the effect of a random process, a stochastic, it's a synonym, stochastic process. This is something that I may ask you at the exam, like what's the difference between a deterministic and a random process? Stochastic, sorry, because it's the pencil is not very okay, even this one. Better. What's the difference between a random and a deterministic process? I may ask this to you, and also I need to make your self-assessment test, and I will put some of these questions to remind you that they may be asked in the exam. When I prepare the self-assessment test, keep in mind that the questions that you find there may be asked in the exam, and plus some more, of course, because in the self-assessment is a closed answer question. So why I'm saying this? Because you don't have to feel uncomfortable if somebody tells you that waves are a stochastic process, are the effect of a stochastic process. So you don't have to feel uncomfortable. It's very simple. When somebody talks to you about probability, or about a random process, a causal process, a stochastic process, it's extremely simple. You cannot predict it with precision. You can only predict it in terms of probability. So this is why I made this long speech, because, you know, when I was a student and I was a young engineer, I was always concerned when people started talking about probability, about randomness. I thought, oh, I don't know this. And it's very, very simple, as I said. It means that you cannot predict, you can just predict in terms of probability. Think about tossing a coin. What can you say? 50% probability of a given outcome. Think about tossing a dice. So you have 6 outcomes. It's very easy to compute the probability of each one of them. Okay. So, let's start talking about sediment transport. And let's start from along-shore sediment transport. I already explained to you the difference between the two. And what is the most effective between along-shore and cross-shore? Okay, so let's say that it depends on the beach, of course, it depends on the weather, but there are some general considerations that we can make, and the first one is that cross-shore sediment transport is mainly takes place during extreme events. So when you have a beach that is destroyed by an extreme event, usually it's destroyed by big waves that approach the beach frontally. While if we talk about long-term changes, usually it's not cross-shore sediment transport that is responsible for it. It's along-shore. Think about the coast of the Adriatic Sea, the Po River delivering sediment, and then the sediment is displaced for hundreds of kilometers. And it's displaced mainly by long-shore sediment transport. And what originates these two types of sediment transport? We said that we focus on wind waves, so these are the main drivers, wind waves. And of course, if you have the direction of waves that is approaching the coastline perpendicularly, then it means that they originate mainly cross-shore sediment transport. If they approach the coastline at an angle, we say, which means not perpendicularly, when we say waves approach the coast at an angle, it means not perpendicularly, then there is an along-shore component that is triggered, originated. Waves originate sediment transport when they break. Okay, let's say that there is also some friction. That's fine, meaning that even if they don't break, when they start interacting with the seabed, there is some friction there, and therefore there is a very limited sediment transport that is originated by friction. Also, we observed recently, these are very recent developments, that at the contact, at the interface between water and seabed, some minor currents originate that are due basically to the effect of friction, and because friction keeps some of the fluid particles, keeps them attached to the seabed, they stop, and therefore there is some friction above them, and some movement of fluid above them, and this movement of fluid, some particles that remain attached to the seabed, some of them that move forward, then originate some minor currents at the contact, at the boundary layer, we say, at the contact between the water and seabed. So there are some minor effects that originate sediment transport, even if the waves don't break, but it's an order of magnitude more less. I mean, these secondary effects are negligible with respect to the amount of sediment transport that is originated by wave breaking. And keep in mind, we are talking about beaches here, okay? So we assume that there are sediments that are available to be moved. So it's extremely important to study where and how wave break. Okay. Now, how can we compute a long-shore sediment transport? Let's focus on it for now. So how can we compute it? So we understood that it's originated by wave breaking. We understand that it's originated by waves approaching the coast at an angle. How can we compute it? So it's an extremely complicated process, as you can understand. And it's a random process. So it's impossible to establish a one-to-one relationship. Even if you give the angle of the waves, if you give everything, it's still impossible, because what happens there? It happens that when the wave breaks, you have a sudden change from a transfer of energy to a transfer of mass. And therefore there is water running over the beach. This water takes some sediment particles, some sand particles, and then brings them forward and then back. And the process is governed by micro-interactions between the particles. It's governed by micro-scale processes. It's governed by turbulence. Turbulence, by definition, is a random process. So it's extremely complicated to describe it. So when you have a process that it's extremely complicated to describe, you understand it, but you cannot describe the geometry, you cannot describe the interaction between fluid particles, because it evolves in a random way. There are basically two approaches that you can adopt. And one approach is to use empirical formulas. And keep in mind, coastal engineering is mainly 90% studied, and design projects are 90% developed by using empirical formulas. Which is fine, I mean, because when you cannot really describe a process with precision, it's perfectly fine that you study the phenomenon in the lab or in an open lab directly on the beach, and then you try to derive empirically a relationship that describes it. What does it mean, an empirical formula? It means that you are basically forgetting in an extreme solution. You are forgetting the physics of the phenomenon. The physics, because this is a physical phenomenon. It's an interaction, it's a movement of a body that is governed by forces. So it obeys the laws of physics. Okay, one may say that there is some thermodynamic because it changes depending on the temperature, but the effect of thermodynamics is negligible. And one may say that there is an effect of chemistry or ecology, because if you have some vegetation floating in the sea, of course there is an effect, but it's negligible. It's mainly a physical process. And this is another capability that you have to gain, to distinguish between different kind of processes, and the difference is dictated by the laws they obey. So when I talk about a physical process, it obeys to the law of physics. If I talk about a chemical process, chemistry. If I talk about an ecological process, ecology, which is related to biology. Thermodynamics, it's different from physics. And then you can have some interactions, so some people say eco-hydrology, for instance, or eco-engineering. It means that they interact between one kind of process or the other, but I would like that you learn how to identify a physical process. So in this case, it's a physical process.